Ladies and gentlemen, today's class recording has started. So, before we started the recording, I kind of mentioned that our next unit deals with atomic theory. The fact that it's called atomic theory should tell you two things, right? It explains why, that's the theory part, and what is it explaining? Atoms, okay? It is explaining atoms and what atoms are. We'll get into that eventually. All right, now, the whole scientific process, right, we started this way back on the first day of school. The whole scientific process is based on the idea of asking questions, gathering observations, and drawing conclusions from those observations as it applies to answering that question. So one of the questions that always comes up, or has come up, for probably as long as people have been asking questions, right, is, what is this made out of? So this rock that I have in my hand, okay? And people make observations, people draw conclusions from those observations, and once we draw those conclusions, we start trying to develop theories. Why is this the answer to this question? So, what is this rock made of? Well, as modern science, quote unquote, is developing, and we, generally speaking, what do we, in our school kind of system set up, not Westlake, but American schooling, right? Where is the, quote unquote, birth of modern science? Where does that happen? No, way before that. So,
Aristotle.
way before that. Aristotle, right? Like ancient Greece is where we kind of start asking better questions. Now, that's sort of our whitewashed version of history and science history and stuff like that. There's lots of really good things scientifically and mathematically that are going on in China. There's lots of good things mathematically and scientifically that are going on in the Middle East, right? And a lot of the European ideas actually come from those places through trade and all that kind of stuff. But, sometimes we don't get the whole story, right? But anyway, so we talk about two theories to answer the question, what is this rock made of? So the first theory we talk about is Aristotle's theory. So Aristotle puts forth a theory that says that everything in the universe is composed of the same four ingredients. And if you know comic books or anime or something like that, these four ingredients will probably sound pretty familiar, right? Air and water and fire and earth, okay? And that gets into the last airbender and all that kind of thing. But this is the concept of these four. The concept of these four elements making up things is not a new concept, but it's something that Aristotle put forth there. And he said that everything in the universe is some combination of those four elements in a different recipe. That this rock has a certain recipe composed of those four elements. And this wood block is also composed of those four elements, just in a different combination. That everything out there is some combination of those four elements. Okay? Now, another ancient Greek philosopher, his name was Democritus. Yeah, but not that. That's not really where it comes from. So. All right. So, Democritus says that if you take this rock and split it in half, you'll have two smaller pieces of the same rock. Same thing, just two smaller pieces. If you took those two smaller pieces and cut them in half, you'd now have four small pieces, but they're all composed of the same thing. If you took those four pieces, cut them in half, now you've got 8, but still the same thing. That you could keep doing that, keep cutting those pieces into smaller and smaller and smaller and smaller and smaller increments, but eventually you would get to the smallest piece of this rock. That this rock is just a big collection of small pieces. Okay? You could also go through that process with this wood block that's up on the table. Keep cutting in half, keep cutting in half, keep cutting in half, and eventually you would get to the smallest piece of this wood block. And this wood block is a big collection of small pieces. Okay? But the small pieces that make up this rock are different than the small pieces that make up this rock. And those small pieces are different from whatever makes up this red stapler. That everything is just a small or a big collection of very, very tiny pieces, but they're all different from each other. Okay? All right. So those are our two theories about the composition of matter. Why are they theories? Why are they theories? Listen. That's not what makes something a theory. Why is it a theory? They're explaining something, right? They're explaining what these things are made out of. But we don't use these theories anymore, right? What did these theories not have? What makes a theory, one theory maybe better than another theory? Proof, let's go with another word instead of proof because that's kind of a weighted word. Facts which kind of do what? Proof is a hard one, right? More evidence, right? The word I was looking for, more like supports that fact, right? Or supports that theory. Right? I know it sounded like that's what you were trying to get to. Yeah. So theories explain things, but theories that we keep using are supported by evidence, right? If you go back, like, talking about ancient Greeks, right? Ancient Greeks have a bunch of myths. And now we just use them as stories. But back in the day, what did those myths do for those people? Explain why things happen, right? Why does the sun move across the sky? Or why does the sun move across the sky? Why? Because some dude rides a chariot, and one of the wheels of the chariot is the sun, and that's how it gets across the sky. Does that explain why the sun comes up and goes back down? Yeah, it does. But is it supported by any evidence? It is not. Right? So, these theories, while explanations for what this rock or this wood block is made out of, aren't really supported by any evidence. And that doesn't change for a really long time. We have a big portion in history where there aren't a lot of scientific developments that occur. We usually refer to that area of history as like the Middle Ages or the Dark Ages or something like that, right? Okay? From like the fall of the Roman Empire to the Renaissance. Yes, if I say that, does that make somewhat kind of sense? Yeah. Okay. So, why doesn't scientific development occur a whole lot during that time? Because of religion, right? This is not a slam on religion, it's just how things go, right? Science is based on asking questions, making observations, and then drawing conclusions from those observations as the answers to our questions. Why don't we make many observations based off of questions in the Middle Ages? Because God made it that way. That's the answer to every question. Why is this rock different from this wood block? God wanted it that way. If that's the answer, you don't have to ask questions, right? And that's not a slam. That's just what happened, right? That's that school of thought, right? Until when? Until the Enlightenment or the Renaissance or whatever you want to call that period of history, right? Where people start asking more questions and not settling for because God wanted it that way as the answer to those questions, right? Okay. So during the Renaissance, during the Enlightenment, that period of time, we start making more scientific discoveries. And we come up with, or we measure and gather evidence for 3 laws. And these 3 laws serve as a big way for us to advance some ideas of atomic theory. First is the law of conservation of mass. I think we're probably all familiar with that. Second is the law of definite proportions, or the law of constant composition. Those two are synonymous. Different name, same idea. And then finally, the law of multiple proportions. Sometimes going back to it's hard to see that, so for purposes of that, you'll have to respond to that, but not everybody. We use them a lot in physics class, so in my other classes, my senior class, we use those equations a lot. All right, good. We got this written down. A couple more seconds. Okay, so let's talk about these a little bit, right? First, I think we're all familiar with law of conservation of mass, right? What does that mean? Mass isn't created or destroyed. How much mass exists in the universe?
We don't know. The same amount that existed at the beginning?
The same amount that existed at the beginning, right? Okay? We never create anything new or get rid of anything. We just rearrange it, okay? Speaking of rearranging, the idea of constant composition. We sort of introduced this in the previous unit, right? Water is a pure substance because it is always the same ratio of 2 hydrogens to 1 oxygen. 2 hydrogens, 1 oxygen. 2 hydrogens, 1 oxygen, always, always, always. That, and we scientifically show through our measurements and through evidence that, you know, in the case of water, it's always 2 hydrogens and 1 oxygen. Always, always, always. Now, the last one, the law of multiple proportions, right? Multiple means many. Anybody familiar with hydrogen peroxide? Hydrogen peroxide is H2O2. It's hydrogen and oxygen, but joined together in a different ratio than water. Same ingredients, different ratio. That gives it different properties. Hydrogen peroxide does not behave the same way that water does, right? Hydrogen peroxide, one of the practical purposes of hydrogen peroxide, not maybe practical, but people use it, right, is to dye hair. It'll take the color out of your hair. Yes, that is bleach of the bleach blonde, hydrogen peroxide. One way to do it. Okay? It kills you. But you shouldn't drink hydrogen peroxide. So we got to turn that. Yes.
Can you put it in your cuts?
Yeah, you can also put it in your cups. Yeah. So yeah, it will serve as a disinfectant and stuff like that. So yes.
What's like the normal bleach that you use? Cheese soap.
Like in your clothes?
Yeah.
Oh, don't drink that. Definitely don't drink that. So, that's hydrogen hypochlorite, I believe is the chemical name of it, if I remember correctly.
Oh, okay.
Yeah, not hydrogen peroxide.
All right.
Hydrogen peroxide, yeah. You can't use hydrogen peroxide to like clean out cuts. It will like kill bacteria and stuff like that. But it will it hurts, yeah. It
burns.
Yeah. But it will also like take the color out of your hair and stuff like that, which water doesn't do. Okay? So, yes.
What is ammonia?
Ammonia is NH3, one nitrogen, 3 hydrogens. So, but it's also, we use it for cleaning solution as well.
Yeah, I'm Audrey.
All right, so a English scientist named John Dalton takes the evidence that is provided by those 3 laws and creates what we refer to today as Dalton's atomic theory. Okay? First, I don't ask you to remember too many names or dates in this class, but this unit, there are a certain number of people that you will need to remember. The first one of them is John Dalton. Okay? So first, he develops his theory back in the early 1800s, right? So when it says developed in the early 1800s, 1803-ish, something like that. Okay? And so he takes the evidence that's provided by those laws that we just listed on the previous page, and and says, okay, if those things are true, those laws, these things must also be true. This is an explanation for why those laws occur. First, all of our chemical elements are made out of atoms. So unlike Aristotle, who said that matter was a combination of these four elements in different ratios and stuff like that, all of them are made of elements. Second, these atoms are indestructible, meaning we will get to eventually the smallest piece of oxygen or the smallest piece of hydrogen or whatever it is that we're trying to break down. Third, these atoms have no electric charge. They are electronically neutral. That will be important on Wednesday when we start talking about different parts of an atom. Fourth, each atom of the same element is identical. So if we have an oxygen atom that is exactly the same as every other oxygen atom that is out there. Okay? And five, these atoms have the ability to come together and make new stuff. But when they do, they always combine together in a whole number ratio. Hold on a second. We have a minute left. I can see the clock.
We have like 40 seconds.
Yeah, you're fine. So,
I'm still listening.
yes, not, but nobody else is. So when I said hold on a second, we have a minute left, that was your cue. Did everybody start packing up?
I'm still listening.
Yes, I see. So when we combine these atoms together, they are, no, most people are not. So we will never find them split into partial atoms. 2 hydrogens, 1 oxygen. 2 hydrogens, 2 oxygen. We'll never find like 2.5 oxygens and 1 1/4 hydrogens. Okay? Yeah, that's true. Right? So tomorrow we'll get into this a little bit more and talk about a couple of very important experiments that advance our knowledge.
Bye, class.